Hi guys, today we are doing a little bit more math with our genetics, and we are going to do some chi-square with genetics. So we've done chi-square several times, but we haven't done any with genetics. You have a chi-square assignment today. It's a page in your binder, and on the back it's got some binomial expansion problems. Those are for tomorrow, so we're just doing that one side today. And actually, we're just going to do the top problem. So I think the top problem is about peas and the bottom problem is about peaches. So we are just going to do the peas today. We will come back to the peaches after we've covered Hardy-Weinberg. So you need a little bit more knowledge to be able to do that peach problem. So just that top problem today. So today's assignment should be pretty short, but you do still have those Punnett squares that you were working on yesterday to finish up as well if you did not finish those. So let's review just a minute. What is chi-square? So a chi-square looks at numbers, observed values, and expected values, and it tells if they are close enough to the same to say that they happened by random chance. Okay? So, for example, if we had a coin and we flipped it 100 times, we know that we should get 50-50, 50 heads and 50 tails. But if you do that, chances are you're probably not going to get exactly 50-50. Maybe you get 48-52. And we would say that's close enough, or 49-51. And so, and if we did a chi-square, that would also tell us that those values are probably close enough, okay? But if you got, say, 30 heads and 70 tails, you would say, whoa, something weird is up here. Something is going on. These results are not due to random chance, okay? These results are from something else. Maybe the coin is weighted, and so that's causing it to land on a certain side the majority of the time. And so that's what chi-square does in a calculation sense to seek to show, okay, or demonstrate. So in chi-square, we always start with a null hypothesis. And our null hypothesis states that the observed values are basically no different than the expected values. So there's no difference, statistical difference, in the observed and expected values. All right, that's what the null hypothesis tells us. So today we are doing our chi-square on corn. So I'm going to scroll up and show you this picture of the corn. So here's the corn. So corn genetics tell us that corn can be purple or yellow. I have some of these corn cobs in my room actually. And they can be wrinkled or smooth, okay? And so in our problem that we have here, it says a large ear of corn has a total of 433 grains. So that's the individual kernels, okay? Including 271 purple and starchy, 73 purple and sweet, 63 yellow and starchy, and 26 yellow and sweet. These numbers, we're going to ignore this about the column 1 and 2. We're not going to do that, okay? So it says, the ear of corn was produced by a dihybrid cross, theoretically, involving two pairs of heterozygous genes, resulting in a ratio of 9-3 to 3-1. And so here's that dihybrid cross. There's those that we talked about yesterday, big P, little p with big S, little s. And multiplying both parents that have that should give us a 9-3 to 3-1 ratio. Okay, so what we are trying to do in this problem is we are looking at these values and basically seeing if they are close enough to that 9-3 to 3-1 ratio that we can accept the null hypothesis and say that there's no statistical difference or no significant difference in those values. Okay, so these numbers here are going to serve as our observed values. The ratio, or what we get from our Punnett square, sometimes it won't give you the ratio. Sometimes you'll have to work out a Punnett square and determine the ratio. But what that tells us is 9-3 to 3-1. Those are our expected values. That's what we would expect based on our Punnett square. And we have to put them together in the chi-square equation. So remember, chi-square is equal to sum of observed minus expected squared over expected. Okay? So this formula is on the formula sheet. I have not given you a paper copy of it. I hope that I have enough sense the next time I put together a paper packet to remember to stick one in there for you. But you can find that on Google Classroom at the very top under class documents. There's a link to the formula sheet. And if you have the means, I would suggest going ahead and printing that out if you can do that at home. But it gives you the formula, but it doesn't tell you how to use it. So it's important that we know how to use this formula. So we do our chi-square, we calculate our chi-square value, and then we can determine whether or not to accept our null hypothesis based on the critical value from our table right here. Okay, so if this is a 9 to 3 to 3 to 1 ratio, then what we have here, the 271 purple and starchy, that would be both of our dominant traits, right? Purple would be dominant and starchy would be dominant. Purple, again, is dominant, and so sweet, if starchy was dominant, sweet must be the recessive, so that's a dominant and a recessive trait. Yellow, that's our recessive, and the starchy we said was the dominant, and then yellow and sweet. And those fit with our 9 to 3 to 3 to 1 ratio. Okay, so we have to turn this expected values, though, into a number that correlates with this. Okay, we can't just use 9 and 3 and 3 and 1 as our expected values. We have to multiply them by 433. So I'm going to calculate the expected values here. And so I have 9 out of 16 should be the first one. 3 out of 16, 3 out of 16, and 1 out of 16. Those just represent simple ratios. And I'm going to multiply each of these numbers by 433. And that will give me my expected values. Okay? So 9 times 433 divided by 16 gives me 243.56. So I'm going to round that up to 244 because you can't have 0.56 of a kernel, okay? So I'm going to round that up. 433 times 3 divided by 16 is 81.1. So I'm just going to leave that as 81. And that'll go for both of those. And then the last one, 1 times 433 divided by 16 gives me 27. And if we add those up, 27 plus 81 plus 81 plus 244, we should, and we do, get that 433, okay? So then we can compare those observed values that I'm just going to write here for easy measure. 433, oh, no, not 433, 271, right there. 73, 63, and 26, okay? So in my chi-square, I'm going to do that 4 times. I'm going to do this calculation 4 times for each of the 4 categories, okay? So I have 4 categories here. So that's also important for being able to determine the degrees of freedom. Remember, the degrees of freedom is the number of categories minus 1. So that's, sorry, I'm not sure what I did there. 4 minus 1. So the degrees of freedom is 3. Okay, and we'll use that in just a moment. So observed minus expected. So I'm going to have 271 minus 244 squared over 244. Just pulling these numbers right here. Observed minus expected. I'm going to keep going. 73 minus 81 squared over 81. 63 minus 81 squared over 81. And 26 minus 27 squared over 27. Okay? And then I have to plug all of those into my calculator. So 271 minus 244 is 27. Squared is 729. Divided by 244 is 2.99. Okay. 73 minus 81 is 8, negative 8. But when I square it, it's going to make it positive. So 64 divided by 81 is 648. I'm sorry, divided by 81 is, let me do that again. I think I messed that up. 64 divided by 81 is 0.79. (63 minus 81 is negative 18. Squared is 324. Divided by 81 is 4.0. And then 26 minus 27 is 1. Squared divided by 27 is 0.04. So when I add all of those up, 2.99 plus 0.79 plus 4 plus 0.04, I get a chi-square of 7.82. Okay, now I added those up. That's what this symbol means. That's a summation sign. It's the Greek letter sigma, and that means you take the sum of all of those. And so then my chi-square is 7.82. But I'm not done, okay? I have to tell you then, what does that mean? So remember, with chi-square, we don't take the square root of it or anything like that. We just leave it as 7.82, okay? So then we have to compare that to our probability table. So here's our probability table. In AP, we always want to use, if I can draw, maybe. Okay, in AP, we always want to use a 0.05 probability. And so what that means is, that means we are allowing for 5% difference in the observed and the expected values. We are allowing for a 5% difference in what we should expect, okay? If it's greater than 5%, then we would reject the null hypothesis. So going back to the quarter flip that we talked about at the beginning of class, that means that it would allow you to be off by 5%. So we would expect 50-50, but if you got 45-55, then that would be within that 5% difference. And so that would be acceptable. Anything beyond 45-55, like 44-56 or 47-43, that would be too big, okay? And so you wouldn't be able to accept the null hypothesis based on those values, okay? So 0.05 probability gives us this number at 3 degrees of freedom. Remember, we talked about degrees of freedom right here. And this number is referred to as our critical value. So we're going to compare our chi-square value with our critical value. And they are, in this case, the exact same, okay? And so because it is less than or equal to our critical value, we would say that we can accept the null hypothesis. It has to be greater than the critical value to reject the null hypothesis. And I didn't realize that this one was going to turn out the exact same. Okay, so we will accept the null hypothesis here, which means that this falls within an acceptable range, that we can say with 95% confidence, because we use a 0.05 probability, that means we can say with 95% confidence, allowing for 5% error, that our values are due to random chance, okay? So that means that based on our chi-square, that the parents were really big P, little p, big S, little s, okay? So don't just say the accept the null hypothesis, you have to explain why. Because the critical value, because the chi-square is less than or equal to the critical value of 7.82. Okay? Most of the time, it doesn't turn out exactly equal to. I think in all my years of doing chi-square, this is the first problem, and I hadn't done this one before I did it with you, that turned out exactly that way. So most of the time, they are slightly different. But generally, if it's less, you accept the null hypothesis. If it's greater, you reject the null hypothesis. If it's equal, you can also accept the null hypothesis because that means it falls right at that 5% mark. Okay? And so we would accept for that reason. All right. If you all have any questions, let me know. And if not, then you all have a great day.